This is about the Everest Group. Briefly, we empower enterprises to resolve their unique business challenges and seize emerging opportunities. Our problem-solving, forward-looking approach is designed around your journey so you can make better decisions. As you can see, we are spread far and wide, and our relationship with clients spans over 3 decades and more. They have continued to stay with us. As you can see, our renewals are at 90%. Let's go to the next slide, please. Thank you. So this is specifically about the Advanced Sci-Tech Group. Basically, when business success is dependent on making smart and confident decisions, how do you navigate and understand the complex scientific and technology advances and innovation that will shape your business for what comes next? That's where Advanced Sci-Tech team identifies emerging science and technology discoveries that will have an impact on your business over the coming years, providing you with unparalleled foresight to make better and more confident decisions. We do have deep pockets of understanding in the areas marked here and cover innovations as it happens in any part of the world. Next slide, please. Thank you. So the agenda slide here, I'd like to draw your attention that without better batteries, the clean energy transition stalls. Emerging battery technologies are redefining the energy landscape with safer chemistries, their cost reduction potential, higher performance, and leveraging sustainable materials. So today's session is structured to give you a comprehensive view of the emerging battery technology landscape. We'll begin by exploring today's battery industry and understanding current technology KPIs, market positioning, strengths, and limitations. Next, we'll dive deep to profile innovative battery technologies such as solid-state batteries, sodium-ion batteries, and other advanced chemistries that are pushing performance boundaries and addressing current industry limitations. We will also examine application scenarios for these emerging batteries, along with their patent activities. Special emphasis will be placed on newer opportunities arising in the context of today's AI-driven era. Especially, we'll also look up at opportunities that come up in data centers, as it's very topical with investments coming from a large number of players around the world. Finally, we'll share insights into industry roadmaps and strategic directions, offering practical recommendations for organizations aiming to successfully navigate and capitalize on the rapidly evolving energy storage segment. That said, we will conclude our discussions by opening the virtual floor for questions, so feel free to use the Zoom Q&A panel anytime. With that, I now call upon Srinivas to do the next slides.
Sure. Thank you, Anand. So today's energy landscape is being revolutionized by batteries, and they are enablers of decarbonization, both in transportation as well as in power grids. And with countries racing towards their net zero goals, the electrification of transport picking up speed, as well as renewables expanding like never before, the battery demand is not just rising, it's about to skyrocket. And it is reshaping the entire energy economy as we know it. According to IEA, International Energy Agency, the global battery market, which is currently valued at around 120 billion US dollars, it is projected to triple by 2030. And lithium-ion batteries are dominating the market today, and they are doing so for a good reason. Over the past decade, the lithium-ion technology has seen dramatic improvements. The costs of these batteries have reduced by about 90%. So they've reduced from around, say, 1,400 US dollars per kWh in 2010 to around 130 to $140 per kWh recently. So this is almost 90% reduction in cost. And while this was happening, the performance and specifically the energy density has steadily improved. Energy density, as you may know, it measures how much energy a battery can store relative to its weight. So it's measured in WH per kg. So because of lithium-ion batteries' high energy density and decreasing cost, they find applications widely from power tools to electric vehicles. So they have been the workhorse enabling our current electric revolution, but this dominance is only the beginning of the story. And as we will see during this presentation, lithium-ion isn't perfect. And the new battery technologies are emerging to push the envelope further. Can we move on to the next slide? Yeah. So as we kick off, we've launched a poll here, and we want to get your insights on most critical challenges in front of the battery industry today. So please vote. You can vote for multiple options. What do you think are the most important challenges for battery today? Right? Very interesting. I see some of you are leaning towards safety. Some of you are also voting for limited energy density. Also, I can see that supply chain constraints as well as high battery costs are also getting some traction here. So keep voting and let's see where this takes us as we transition into discussing the post-lithium-ion innovation. Yeah. Can we share the results? Right. So if you look at this results, you can easily see that the cost is a winner. It has emerged as a top concern, and safety as well as energy density are also very, very close behind. So this kind of underscores the multifaceted challenges where these are the challenges we face when it comes to lithium-ion batteries. And this kind of sets a perfect foundation for us to explore emerging technologies like solid-state batteries, sodium-ion batteries, which we are going to cover during this webinar. We can move on to the next slide. Thank you. So here we confront a very, very critical question. If lithium-ion batteries have been so successful, why do we need something else? The answer here lies in several challenges as well as limitations that lithium-ion batteries face as we push the boundaries of what we need from an ideal energy storage solutions. So let's break down the key challenges. So very, very important thing is today's lithium-ion ecosystem is built on a concentrated and fragile supply base. 80% of global lithium supply comes from just 3 countries, Chile, Australia, and China. the DRC, Democratic Republic of Congo, alone provides about 70% of world's cobalt, and 50% of global battery manufacturing capacity is concentrated in China. So all of this combined together, this concentration poses major risk, and this risk is from price shocks, trade restrictions to ESG issues for labor as well as for mining. So geopolitical as well as price volatility risks are huge, and relying solely on lithium-ion batteries could mean that our electrification plans can hit a resource wall. The other important challenge here is with energy density. Lithium-ion batteries are approaching their theoretical limits when it comes to energy density. Practically, they provide around 230 to 240 Wh per kg when it comes to energy density, and their theoretical limit is around 350 to 400 Wh per kg, and this restrict the effectiveness in applications which would require high energy density. So those applications can be long-range EVs or aviation, so on and so forth. And there are incremental improvements happening within lithium-ion batteries, like adding silicon to anodes or using high nickel cathodes. And with this, they are improving the energy density to a certain extent, but we are not expecting lithium-ion to suddenly double the energy content. And this becomes a major problem for lithium-ion batteries for certain applications. Another challenge is safety of the battery and thermal runaway. So despite their widespread use, the lithium-ion batteries can be volatile. Fire risk always remains a serious issue as the cells charge and discharge, and especially under stress or damage or harsh environmental condition, they can overheat. And in a worst case scenario, the flammable liquid electrolytes which lithium-ion batteries use, it can ignite, which leads to a cascading thermal runaway, and the fires can happen. And we've seen electric vehicle recalls, we've seen high-profile accidents as well. And this has made both the public as well as investors in the industry acutely aware that we need inherently safer battery chemistries if possible. There are also challenges with charging speed of a battery as well as dendrite formation. So pushing lithium-ion batteries to charge faster can cause lithium metal plating on the anode, and this is called dendrite formation. And this can short circuit the battery, right? And this is a safety hazard, and this also kind of degrades the cycle life. So while some lithium-ion batteries advertise that they are fast charging, but doing so repeatedly can stress the battery, and there is a limit to how fast we can safely charge today's lithium-ion battery without degradation. Also, there are sustainability concerns. Today's lithium-ion recycling rates are very, very low. Only about 5 to 9% of lithium-ion batteries are effectively recycled. And even for the ones which are recycled, the material recovery rates are very low. And a huge wave of EV batteries is expected to retire in 2030s. And if we don't improve the recycling technologies and recycling rates, we will have a waste as well as supply problem. And the need for battery recycling, better recyclability, and reuse is a major challenge that current lithium-ion technology has not yet fully solved. So in summary, while lithium-ion batteries have enabled today's electric revolution, they are not without serious challenges. Let's move on to the next slide. Slide after this, please. So the challenges of lithium-ion batteries set the stage for innovation. In this slide, we introduce the emerging battery technologies which are poised to complement or even supersede lithium-ion in various roles or applications. So here we actually pivot from limitations or challenges to the opportunities. This is an introduction to the emerging battery technologies. And you'll see that there are diverse array of new battery chemistries which are in development, and each of these batteries are there with unique advantages. You can see that there are technologies like solid state batteries, sodium ion batteries, lithium sulfur batteries, metal air, and advanced lithium ion variants like lithium manganese iron phosphate batteries. So some emerging technologies within this, they aim to improve on lithium ion by changing the electrolyte or internal design. So for example, solid state batteries replace the flammable liquid electrolyte with solid electrolyte, which will dramatically improve the safety, and it can also potentially allow the use of lithium metal anode for higher energy density. There are other technologies which pursue alternative chemistries altogether, and they will use different elements also. For example, sodium ion batteries would swap out lithium for sodium, which is of course a far more abundant as well as cheap element. So here the idea is to get a battery which might be a bit larger or heavier with a lesser energy density than the lithium ion battery, but sodium ion battery will always be at much lower cost, and it will also have materials which are plentiful in availability. So this actually will be transformative for stationary energy storage as well as cost sensitive market. Then we also have batteries that would go for ultra high energy density, and they do so by fundamentally new chemistry, like say lithium sulfur batteries, where the lithium metal gets paired with sulfur to potentially achieve the energy densities which are several times higher than lithium ion batteries. And there are technologies like metal air batteries, which actually use oxygen from air as a reactant, which gives them much higher theoretical energy density. And consider these as moonshot technologies that could one day allow electric aircraft to compete with fossil fuel range. And also there are incremental advancements within lithium-ion family, which is like LMFP. And this is an evolution of LFP batteries within lithium-ion battery. It's not even a radical departure like lithium sulfur battery, but this is an important incremental change that boosts energy density without introducing any expensive material. And this is a practical, very near-term solution to improve lithium-ion batteries. So in the next part of presentation, we are going to deep dive into each one of these emerging technologies. We are going to look into how they work, what is their working principle, what is their current status, and what potential they are going to hold. And this is where we get a bit more technical, and we also discuss real-world progress application as well as examples. So over to you, Ritima, for the next part of presentation. We can move on to the next slide, please.
Yeah. Yes, thank you, Srinivas. So hello, everyone, and let's dwell a little bit deeper into each of these technologies, right? Let's start off with solid-state batteries. Now, solid-state batteries have been spoken about in the recent past in the context of electric mobility. Now, why electric mobility, right? Now, imagine you have an electric vehicle. What are the certain features that you would require in the battery of your electric vehicle? First, certainly it is about safety, because we hear a lot of electric vehicles that are bursting up into flames. Second, definitely being a compact battery, right? You do not want to bulk up your electric vehicle. And you, of course, do not want to wait out on the charging time as well. Now, solid-state batteries provide all of this. How are they doing this though, right? And when we look at the chemistry of the solid-state batteries, they essentially, as Srinivas had mentioned, they essentially replace the liquid electrolytes within the lithium-ion batteries into solid electrolytes, such as oxides, sulfides, or polymers. The small shift kind of gives it a very high energy density. And by energy density, I want you to imagine, always correlate energy density with compactness. So it essentially means storing more energy, but in a lesser mass. So when we look at the energy density of solid state batteries, they are almost 1.5 to 2 times higher than the conventional lithium ion batteries. Also, they offer 50% faster charging. And this is mainly because of the high energy cathodes and the high capacity anodes. In short, these are high performance components that are used inside these solid state batteries. Along with this, they also give you higher durability of approximately 10,000 charging cycles. They have the potential to provide that much. But at this point, practically, most of the solid state batteries are providing lesser than this. And in addition to this, solid state batteries are also able to operate under wider temperature range. That means even if you're in India or in Europe or in any other colder regions like Alaska, you'll be able to operate solid state batteries in your electric vehicles. Interesting, right? However, they do have a limitation of cost, and they are almost 4 to 6 times more costlier than the conventional lithium-ion batteries. However, their applications are definitely more oriented towards electric mobility, electric aviation, and electronics. And this is majorly because they are able to offer compactness, safety, and faster charging. Now, there are many innovators in this space, and QuantumScape is one of these innovators that have already licensed out their technology. QuantumScape is a pioneer in solid state batteries, and they have licensed out their technology to Volkswagen to commercialize solid state batteries in another 2 to 3 years. Can we move to the next slide, please? Next in line, we have sodium-ion batteries. Now, I want you to think of just one word when I talk about sodium-ion batteries, and that is cost efficiency. Now, sodium-ion batteries essentially they cater to one of the major challenges of lithium-ion industry, which is lithium being a critical metal or metal that has limited availability. But sodium, on the other hand, is, believe it or not, 1,000 times more abundant than lithium. So why not replace this lithium with sodium, right? And on top of that, because of this abundance, it also caters to the supply chain barrier reduction, which directly affects to the cost. So it is 20 to 30% more cost effective than conventional lithium batteries like LFPs. And with their cathode options such as layered oxides, Prussian blue analogs, and polyanions, they're able to offer 90% capacity retention as well at very lower temperatures. The only cost element, however, in sodium-ion batteries comes from the anode. Sodium ions do not very well intercalate with the graphite, unlike the lithium ions. And so they have a tendency to intercalate with hard carbon or titanium-based oxide, which adds on to the cost. Despite that, the cost of sodium-ion batteries are lesser than conventional lithium-ion batteries. If you look at the applications, though, they are limited to stationary energy storage. But why? The answer lies in the limitation of sodium-ion batteries, which is lower energy density. Now, let me give you an example from some of the innovators. Just last month, BYD and CATL have developed or have announced that they are going to commercialize the sodium-ion batteries. And these sodium-ion batteries have an energy density of almost 160 to 180 watt-hour per kg. Now, when you think about what Srinivas had said, this is much lower than what lithium-ion batteries are able to provide. But despite that, sodium ion is gaining traction. And that is, as I said before, just remember, it's the cost efficiency, right? Let's move on to the next battery. Can we move on to the next slide? Yeah, thank you. The next battery in line is lithium-sulfur batteries. Now, look at the theoretical energy density it's able to offer. Almost 2,600, which is 5 times more than the conventional lithium-ion batteries. But how are these lithium-sulfur batteries able to offer such high energy densities? The answer lies in the details, right? In this case, the answer is in its chemistry. So when you look at it, when you look at a lithium sulfur battery, there are multi-step reduction reactions that are happening within the lithium sulfur batteries, such that it's able to transfer almost 16 electrons overall within each of these reactions, like together in these reactions. And this kind of electron transfer has not been seen in any of the other batteries. Because of this electron transfer, it's able to charge, it's able to store and dissipate more charge, which is increasing the theoretical energy density. On top of this, it is using sulfur, which is an abundant it's an abundant element, and because of its low weight, it's also able to reduce the cathode weight up to 40 to 70%. And if you look at the applications, as I said, as an energy density increases, compactness increases, and so the applicability is more towards electric mobility and electric aviation. Now, there are many innovators who have been working on LSB batteries as well. For instance, Zeta Energy has already commercialized, rather in the pre-development stage, not commercialized, but pre-development stage, where it is already developed a proprietary 3D structured anode and a sulfur carbon cathode based lithium sulfur batteries, which is able to offer 450 watt-hour per kg. And if you remember what Srinivas had said, it is higher than what the lithium-ion batteries' theoretical energy potential is. So you understand the importance of this LSBs as well, right? We can move on to the next interesting battery technology. Thank you. So now we are going to talk about a very interesting battery candidate here, which is the metal air batteries. It uses, as the name suggests, metal as well as air, and within the air, it is able to use oxygen. Now, the interesting part is, as we replace the metals within the metal air batteries, the application diversity also changes. For instance, if I choose to replace this metal into lithium and make it a lithium air battery, we see a very high theoretical energy densities of 11,400 watt-hour per kg, as opposed to lithium-ion batteries that are practically offering 250 watt-hour per kg. On the other hand, if I replace this metal with iron, and let's call it iron air battery, in that case, it's offering a new advantage of higher storage duration of almost 100 hours, which is a multi-day storage. And this has been one of the challenges of storing renewable energy. Now, the choice of these electrolytes that are used within these metal air batteries are dependent on the reactivity of the metals. The higher reactive metals are the metals that have higher reactivity. If they are used, then the electrolytes could be non-aqueous, whereas on the other hand, if it's less reactive, then alkaline aqueous electrolytes are needed. And as I said, that with the metal comes diversity in applications. So you can see the applicability in electric mobility, electronics, stationary storage, grid stabilization, etc. And when we look at the innovators in today's world, Panasonic Energy has already commercialized zinc air batteries, which are used in wearables. Whereas Form Energy has pioneered the iron air batteries, which are able to offer up to 100 hours of storage duration. And they are going to go into commercialization very soon. And when we look at Toyota, Toyota is working with the lithium air batteries as well. Now, moving on to the, can we move to the next slide, please? Now, moving on to LMFP batteries. Now, LMFP batteries are nothing but an upgrade for LFP batteries. And let me explain you how. So it's just that one letter M, which is manganese. So it is lithium manganese ferrous phosphate, which means that instead of entirely iron, it is able to incorporate manganese as well. And what this addition of manganese does is it allows the battery to work in distinct voltage levels. So because of the iron and manganese, there is distinct voltage level, which overall results in a higher operating voltage of the batteries. So you can see it's almost 0.5 volts higher than the conventional LFP batteries. This kind of jump, and when it is combined with the stable olivine structure of the LFP batteries, kind of offers a higher energy density of 15 to 20%. And also it provides a 75% capacity retention in lower temperature as opposed to 60 to 70% in LFP batteries. It is important to note, however, that the manganese to iron ratio is very critical here. If you actually have a lower ratio below 50 to 65%, then it will be an underperforming LMFP. Whereas if you have a ratio which is 50 to 65% more manganese, more than manganese, then it is going to have or risk side reactions. And the applications are very similar to LFP. So basically almost all of electric mobility, aviation, electronics, stationary storage, etc. With its few limitations which are very similar to LFP batteries, innovators that are contributing to or trying to capture the market of LMFPs are those that are already existing in LFP segment. So you can see BYD, CATL are already market leaders in LFP batteries. We can move to the next slide, please. Yes, so we have already spoken about the core emerging technologies that have that are going to contribute to the future of battery industry. But there have been a few batteries that have been supporting this industry for some time now. And just to give you some examples, for example, flow batteries and liquid metal batteries, they are catering to the long duration storage. Whereas nickel zinc batteries and zinc ion batteries are catering to different advantages. Let me give you another example here. When we talk about nickel zinc batteries, the nickel zinc batteries are known for their higher power density. What I mean by this is it's able to provide spur of power to the equipment and for a shorter duration time. Does it sound familiar? Have you noticed what our UPS batteries are made of? They're usually lithium or lead acid, but nickel zinc batteries are coming up in that space, and they are able to offer better advantage than lithium ion as well as lead acid batteries by offering lower footprint as well as by offering better power density, and thus they have become very important in data centers and telecommunications. With that, I think we have come to the end of the discussion in terms of detailed battery technology analysis. And let me hand over to Srinivas to take up for the comparison slides as well. Thank you.
Thanks, Lithium. Yeah. So when it comes to current battery industry, we do expect lithium ion to remain dominant for short to medium term. At the same time, emerging chemistries are carving out specialized roles which reflect their unique performance advantages. So if you look at this slide, which is in front of you, it provides a comparative analysis of these battery technologies, benchmarking each against key performance indicators, KPIs, such as cost, energy density, safety, cycle life, and so on. So you'll see that each of these emerging battery technology, it excels in some areas and it has weakness in others. For example, solid state battery is great for safety and energy, but has some challenges when it comes to cycle life and a major challenge when it comes to cost. Sodium-ion battery is great for cost and safety because the materials which required are non-toxic and abundant, but it suffers with lower energy density. Lithium-sulfur has amazing energy density. It also has a good cost profile, but it needs major improvement when it comes to cycle life. Metal air battery is the technology when it comes to energy storage, and it also uses very common materials, but it has major challenges when it comes to cycle life. And LMFP, which is an immediate improvement, which balances kind of cost and performance. And because it's an incremental improvement, it can also fit into existing lithium-ion production lines without much change. So within the battery engineering, it's often said that fast, cheap, or high capacity, pick two. So the technologies which we discussed today, they juggle these trade-offs in different ways. And that is why we foresee multiple chemistries coexisting. One technology can be chosen for maximizing range of electric vehicle, another technology for minimizing cost, and another for safety critical use as well. So we are entering into an era where we optimize the battery chemistry per application rather than trying to force one solution into all usage. So let's move on to the next slide. Slide after this, please. We can actually skip 2 slides. We can skip this as well. Lithium-ion has actually covered the electric vehicle as well as energy storage application. Let's move on to the next slide, the AI. Yeah, I want to spend some time on this slide. So let's focus on a very, very critical and emerging application for batteries. As the AI era accelerates, the data centers are becoming one of the fastest growing energy consumers globally. And they are placing immense stress on energy grids, energy markets, as well as sustainability goals. Data centers today, actually, like 2 years back, data centers used around 460 TWh of power. And by 2026, they would exceed around 1000 TWh, which is more than double in just 4 years. So we are already seeing aggressive investment in energy strategies from companies like Amazon, Google, Microsoft. We are seeing strategies like including renewable battery-backed microgrids. We've seen strategies even like small and modular nuclear reactor options. Microsoft actually has goals to eliminate the diesel gensets entirely by 2030. And with all this, there is a strong push to deploy massive battery systems for data centers. So when it comes to battery technologies for data centers, the priorities are absolute reliability, long calendar life, and high power on demand. So when the power goes out, these batteries must kick in instantly and provide huge power draw in a short time. So safety as well as reliability are very crucial. Reliability measured by uptime. So data centers would require 99.999% availability. This prevents costly outages. So a single blackout event for just 1 hour can cause losses up to $100,000 or more for hyperscalers. This makes resilience, reliability of batteries and backup power a very, very critical and important KPI. So what are those battery technologies which are going to lead in this AI era? Solid state batteries are best suited when it comes to high energy density server farms. LMFP batteries are ideal for co-location centers, and sodium-ion batteries are suitable for backup systems in price-sensitive regions. Let's move on to the next slide. Right. So the patent landscape, when it comes to emerging battery technologies, if we look at the duration from 2021 to 2024, it clearly shows that China is leading the global race when it comes to battery innovation. It accounts for more than 78% of all patent filings. That's a huge number. It's a dominance. Over 90% of all the patents which were filed, those were invention patents, which reflects deep technical R&D as well. It's not just minor changes or incremental innovation. These are reflecting deep technical R&D. And more than 60% of the patents are still in pending status, which indicates that in near future, there is a robust pipeline of innovations which are yet to be commercialized across all these emerging battery technologies. And when it comes to assignees, there are key players which include LG Energy Solution, companies like Toyota and Guangdong Bump Recycling, and they are showing how OEMs are investing heavily in next generation battery. So ultimately the companies, not just companies, even the countries that dominate the patent search, they will have a strategic advantage. They are going to shape the trajectory of battery innovation, and they're going to secure their influence over this energy transition for coming decades as well. Let's move on to the next slide. Next slide, please. Right. So in this final section, we are going to shift our focus towards strategic roadmap, which is roadmap ahead, the roadmap of evolution of these technologies, and what the organizations and the ecosystem players can do now to prepare, participate, and lead in the battery revolution. So the roadmap kind of outlines how next generation battery chemistries are expected to progress and evolve over the next decade. In the short term, the focus, you can see that the focus is going to be on chemistries like sodium-ion batteries and LMFP, and these are already very close to commercialization. And this particular period, the immediate future period, is about stabilizing the battery supply chain by reducing the reliance on geopolitically sensitive materials like cobalt as well as nickel. Both of these chemistries actually offer cost efficiency, and they actually have a very, very solid safety profiles. And this makes them ideal for grid scale energy storage, as well as storage for residential applications. In the next phase, from 2027 to 2030, in this phase, we will see lithium-sulfur batteries as well as metal air batteries begin to mature. And these are the chemistries which are chemistries performance driven. So LSB is lithium sulfur battery. It offers ultra high energy density, and metal air batteries actually deliver long duration energy storage at low cost. And both of these technologies, their value lies not in replacing lithium-ion batteries across the board, but they will actually replace a part of lithium-ion batteries in specific use cases like aviation, drones, or future grid storage. And from 2030 onwards, we anticipate solid-state batteries will become mature, and they will be a defining technology for premier electric vehicles, aerospace, as well as high-performance electronics. So by that particular stage, after 2030, we expect many of today's problems or hurdles for solid-state batteries like dendrite formation, manufacturing cost, as well as scalability limitations, all of these challenges will be largely addressed. So this particular roadmap actually tells us that the battery innovation is following a phased adoption curve, where we see the cost-first technologies are going to scale early, and they will be followed by high-performance solution, which will enter either premium or high-demand segments. Let's move on to the next slide, please. Right. So now we've seen the science, we've seen the roadmaps, and we've seen the innovations as well. But this particular slide brings us to the most important question. What are the key shifts the organizations will have to do, and what should you do to be successful? We've discussed that battery demand is no longer emerging, right? It's exploding between EV adoption, AI infrastructure, renewable energy storage. The global battery demand is projected to triple by 2030, and this growth is already driving intense competition for materials, competition for IP, as well as talent. And we are actually not preparing for the future, we are in the future. So what strategic moves should the organizations make today to effectively navigate and lead in the rapidly evolving energy storage landscape? First thing is, the organizations should scout emerging chemistries aligned with specific market verticals. Don't wait for one winner, build a portfolio. Also, partner with us to scout, partner with us to de-risk innovation, and gain early access to proprietary breakthrough Reach out to us today to explore how we can collaborate and how we can drive your success in the next era of energy storage. So you can use now the question and answer panel from your Zoom window to submit if you have any questions. We will answer as many questions as we can, and we can also follow up with others directly after the session. Thank you. Over to you, Anand.
All right. Thank you, Srinivas, and thank you, Riddhima. Let me now see the questions that they have come. Yep, there are some interesting questions that are up available. I'll leave it to either you, Srinivas, or Riddhima to take these. The question, let me call this out. Are we seeing a realistic shift towards friendshoring or reshoring battery production, especially for next-gen chemistries?
Oh, friendshoring or reshoring? Very, very interesting question. We've heard about nearshoring as well, right? So are we actually seeing this shift towards nearshoring or friendshoring? Yes, but it's very, very early. It's too early, and it's also uneven. Meaning these technologies, most of these technologies are at early stage. And we've seen trade tensions, especially with China controlling more than 80% of global battery material refining. These tensions are actually pushing countries to friendshore as well as reshore the production. But for next generation chemistries like solid state batteries or sodium-ion batteries, the shift is not just to avoid the risk, but also building entirely new supply chains, because some of these are inherently new chemistries altogether. And we've seen some examples, top of my mind, QuantumScape, which is a known player when it comes to solid state batteries. They are building a solid state battery facility in California with Volkswagen's backing. But they will still have to rely on Asian suppliers for key materials like solid electrolytes. So nearshoring or friendshoring is possible, but the challenges do remain. Technologies like solid state batteries actually need specialized ceramic or sulfide electrolytes, where we will need to require, or we will need to depend on other regions for the product. But the bottom line is the friendshoring is real. But for next generation batteries to scale globally, we first need more than relocation. We need diversified innovations hub so that we can go at the commercialization or scale level first. So the mantra is diversified innovation hubs first, and then nearshoring facilities for supply chain. Hope that answers the question.
Also, thank you for that. The next question is about, I think you briefly covered about this on recycling methods, but here's the question. As new battery types are developed, can today's recycling methods handle them all? Or will we get stuck with processes that only work for older chemistries?
Right. Yeah, again, a very good question. There is actually a real risk that current recycling methods, shredding, after shredding, hydrothermal process, or even pyrometallurgical process, both these processes could become outdated if the new battery chemistries like, say, solid state batteries or sodium-ion batteries become widespread, because currently these methods and these processes are optimized for lithium-ion batteries with cobalt, nickel, as well as graphite. So if the new battery chemistries are going to use different material or have different structure altogether, like solid electrolyte, existing recycling lines may not be efficient, may not have high recovery rate as well. However, there are some recyclers, there are some technology providers which are just about to start the recycling design for chemistry agnostic processes. So staying adaptable is going to be the key to avoid lock-in. and ensuring the recycling remains cost effective, and also they will have enough market to play in. We've already seen companies like 24M Technologies. They have developed recycling technologies for semi-solid EV batteries, which is a type of solid-state batteries. So, of course, the industry is thinking on those lines for sure.
All right. Thank you for this, Srinivas. Are there any other questions that are there? Let me just go and check them. There is a general question about what do government agencies do to encourage these shifts towards innovative battery chemistries?
Yeah. Again, batteries, especially the emerging battery chemistries, would require policy supports. Any new technology for that matter at initial stage, because the scalability is not there, because economies of scale is not kicked in, cost efficiency is always the issue. So governmental support, subsidies, or tax benefits, these are some of the incentives governments can offer and drive the innovation when it comes to emerging battery technologies.
All right, so that sounds good. I think we are up almost on the hour. Our sessions, of course, next is that we do have the Engage event coming up. And Everest Group, of course, is... can we go to the slide on the Engage, please? Yeah, there you go. So we have an interesting event coming up between September 8th to 10th. That's on actually educating executives in the global business services space, global sourcing, vendor management, procurement, and shared services. So mark this date. We had phenomenal success when we conducted this event in 2024, and we look forward to hosting this event again on between September 8th to 10th. We expect almost about 450 plus attendees, and you will have direct access, of course, to the Everest Group's analysts, and it's at the Renaissance Dallas Hotel in Dallas, Texas. So thank you for this. If there are any other questions, please feel free to reach out to us, and we'll be more than happy to address them. So with that, we conclude this session. Thank you all for joining.
Thank you, everybody. Thank you.